Hey team, I'm Maddie. Welcome to Science Side Up. And today we're going to continue our discussion of climate feedbacks by talking about water vapor feedback. Okay team, to understand water vapor feedback, we need to understand two things about water vapor and what it does in the atmosphere. The first thing is that warm air can hold more water vapor in it than cold air. So think about if it's winter and you live not in the tropics, but you live, say, in the mid-latitudes like I do here in Oklahoma. In the winter, my skin on my knuckles gets cracked and really dry because the air is so dry, right? We tend to think of winter air as this cold, dry air, and in the summer it's hot and humid. So the reason that it feels that way is because warm air can hold more water in it than cold air. This is because of something called saturation vapor pressure, and that thing is a function of both pressure and temperature. So what that is, what saturation vapor pressure sort of describes are the conditions necessary for water vapor in the atmosphere to condense into a liquid and form something like clouds or dew. In warm air, you can have a lot more water vapor in that air before it's going to be forced to condense out versus cold air. Cold air can only hold a very little bit of water vapor. The second thing I want to talk about is actually a common thing that climate skeptics or climate deniers like to bring up, and that is water vapor is a greenhouse gas. So water vapor is going to interact with the outgoing long-wave radiation from Earth's surface in the same way CO2 does. It's going to absorb it and then reflect it back down, well, reflect it in all directions, but aiming some of it back down to the surface. This is where the climate skeptic would say, well, if water vapor is also a greenhouse gas and there's so much water vapor in the air, why is that not something scientists are freaking out about? Well, that's because turns out there's a whole lot of water here on planet Earth, and there has been for a very long time. So the water that's in our atmosphere versus in our oceans and rivers and glaciers, that's in a kind of happy equilibrium balance. And when we get too much water vapor in the atmosphere, we get clouds and precipitation. So that also means that water vapor in the atmosphere doesn't have a very long residence time. Remember that residence time is how long can this type of molecule or this type of gas exist in the atmosphere before there's a process that removes it. Because of that short residence time, water vapor in the atmosphere, if we chunked a bunch of water vapor into the atmosphere tomorrow, it would not take very long for that system to kind of reset itself. It would remove that water vapor through clouds, precipitation, things like that. Bringing those two ideas together, warm air holds more water vapor than cold air, and water vapor is a greenhouse gas. That's gonna let us draw our nice little flow chart, just like we did for the Ice-Albedo effect. So let me get my colorful happy chalk. Again, we're gonna start with surface temperature. Surface temperature is going to affect atmospheric humidity. Atmospheric humidity affects long-wave radiation. And I did go ahead and just say upward long-wave radiation. As we did with the Ice-Albedo effect, let's see what happens if we increase surface temperature. Increasing surface temperature means our atmosphere is going to be warmer, means it can hold more water vapor. So that's going to make my atmospheric humidity go up. So we have a positive connection between these two terms. If I have more water vapor, more greenhouse gases, that's going to increase that long wave radiation. So this guy goes up as well. So we get a positive relationship here. And last but certainly not least, more Radiation means higher surface temp. So again, we get this positive relationship, a nice positive feedback loop. And we see that an increase in surface temperature through the water vapor feedback will result in even warmer surface temperatures. Where is this effect important? The short answer is everywhere, but it's important in the tropics and the polar regions kind of for different reasons. It's important in the tropics because we already have a lot of evaporation going on. It's already pretty darn warm there. So if we make it even warmer and we can hold even more water vapor, that's going to definitely be a driving force in the tropics. But it's also important in the polar regions because the polar regions are very, very dry. So adding some extra water vapor, we're gonna kind of notice it pretty quickly. Now, this isn't as important an effect in the polar regions as the ice albedo effect, but if we're thinking 100 or 200 years down the line with constant or continuing emission rates, this would become much more important in the polar region once all the ice is gone, if that kind of makes sense. To sum that up, water vapor feedback is important everywhere. Where it's right now the most noticeable is going to be the tropics, but that could change in the future. Okay, team, that's all I've got for you guys today. I hope you are well. I hope you enjoyed this video. Come back next time for even more climate feedbacks. In the meantime, don't forget to like, subscribe, be kind, and I'll see you all next time. Bye, team.